Hello guys, welcome back. So this video discusses about the UART loop-back exercise first. Thanks for voting on the community poll. Not just that UART1 loop-back exercise got maximum votes. It also makes sense in continuation from the previous video. Second, I would highlight some of the key changes in code since the last video session. And finally, I would brief or provide an introduction on what next video is going to be. So stay tuned and click the subscribe button if you are interested in future RISC-V videos. And don't forget to like or dislike the session. Okay, let's jump in. First, let's see the UART1 loop-back exercise. So for this exercise, make sure that you have the UART1 transmit and receive pin looped back or shorted so that the data that is transmitted through the UART TX pin is passed back to the RX pin to be able to receive through the same UART. Okay. So in this exercise, what I'm trying to do is fill a transmit buffer with a series of numbers starting from this address and start transmitting from this address through the UART1 TX pin. And since it's looped back, the same data should be able to be received from the UART1 RX pin, and I'm storing it back from this address onwards. So very first, before we execute this exercise, the receive buffer should be filled with some random data, and the transmit buffer should be initialized with a series of numbers or data, whatever you want to transmit. Whereas in this exercise, I have filled with this series of numbers. Okay, so if you go to the GitHub repo, so I know that I have the second part to cover few of the recent changes, but this one I have to mention now because that's part of this loop-back exercise. If you see here, there are two branches now. One is the main trunk, and the second one is the vectored trap. So I have created this vectored trap branch new just for this exercise, and soon I will merge it back. But this loop-back exercise I'm running from this this branch. Okay. So now if you see the UART1 loop-back application, so this is the GPA-UART21 on-off application, and the UART1 TX application, which we saw in the previous session, is this one. And the new application which I have created is the UART1 loopback, and which has this file. So as I mentioned before, so this is where I fill the series of numbers into the TX buffer. Okay, so the TX address is set to 8 followed by 3 zeros and 2 followed by 3 zeros. This is the TX buffer address, and this is the RX buffer address I'm using in this application. Okay, so the value whatever you use here, make sure that that's a valid range, and these are all in the RAM address range. So I'm good to go. And one key difference would be that I'm not using any interrupt here in this loopback exercise. Instead, after enabling the transmit and receive, once the TX buffer is filled, I start transmitting from this address, and I use this logic to reset the address back. So what happens is, so from this address onwards, all the bytes, one by one, these bytes are transmitted. Then once it reaches this 2020, or once the address of 8 followed by 3 zeros and 3020. So whenever the address reaches uh, 32 bytes from the base, it's resetted back to the first address with this logic. So what I do is just do a bitwise and with this bit alone set as 0. So when you AND this with this value, it would become 0 here. So it is like the very first address. Then it would again increment by 4 bytes and keep fetching the next bit. So the main purpose is that even if you run for any number of times, it will always just keep looping within the first 8 bytes of the receive and the first no, yeah, first 8 data of the TX and RX buffers. I do not want this to overflow. That's the only reason I do this. Okay, so this is the main loop. So there is a transmit and a receive loop. So it would keep transmitting until the TX FIFO. So apart from this transmit buffer in memory, which I use here, there is a TX FIFO, which is part of the UART peripheral. So until that is full, this would keep transmitting. And then if that is full, it would jump back to receive, and it would keep receiving until the receive FIFO is empty in the UART1. So it will be just jumping back between transmitting and receiving. And it would never get out of this app loop TX and RX. Okay, so that's the crux of this application. So let's go ahead, build and run and see if this works. I'm sorry. First, I set a breakpoint at the start of this loop so that we can investigate or examine the initial data on those memories. So okay, let me run. Okay, so first, initially the TX buffer had random values, and once we executed up to this loop, so this is where you can see that TX buffer or the TX address from that onwards. So the value is incremented by 1, and stored into the consecutive memory locations. Okay, and now if you examine the receive address, so receive address or the receive buffer still has the random data. So now let's delete the breakpoint and Control C. Okay, so you can clearly see that the data, whatever is transmitted, is looped back and received and stored back into this memory. Okay, so even if you run for any number of times, it wouldn't overflow. Still, it would just keep looping back into this same or overwriting the same memory locations. Okay. So that's about the UART1 loop-back exercise, and you can always get the latest code and make sure that you have the UART1 TX and RX pin loop-back. Okay, so let's get onto the recent changes I have made in the Git repo. So the major or the key change in the code after the last session was on the trap handling. So in RISC-V, so exceptions and interrupts are categorized as traps, and we are not discussing about exception now. On the interrupts, it can be configured in two modes. One is the direct mode, and other one is the vector. So till the previous session, I had that trap handling in direct, in which case for any interrupt source or for any interrupt source ID, the execution would jump into the MTVEC base address, and within that, it's the user duty to find what is the source for the interrupt. Then within that, you have to check and then process it accordingly. Whereas in the vectored interrupt mode, for each source ID, so these are all the valid and the right source IDs of source IDs in Hifive1 revision B board. So the source ID 1 correspond to AON always on watchdog and always on RTC and so on. So source ID 4 is for UART. So this is how the uh, source IDs run, and vectored trap address, or whenever the interrupt occurs, the jump address would be like the base address, which is there in the MTVEC, plus 4 times the source ID. So for source ID 1, this would be MTVEC plus 4, and for UART 1, it's going to be MTVEC plus base address plus 16, and so on. So okay, so which means that for GPIO, GPIO 21, MTVEC base address plus 116, that would be the jump address for the GPIO 21. So if you see the code here, what in the vector, that's why I have created the branch named vector trap, and in the vector trap I would have created two trap handling. One is the direct, so I have created a config.s file, you can configure either the code to run in the vector mode or direct mode. So in vector case, this file would be compiled. You can see here on top, that would be an if def. And in vector mode, you can see the empty vector table I have created. So this section, let me see the LD script. I have created so I have put all the section into this, and from the start, so this would be the base address and for source ID. So when UART1 interrupt occurs, or let's take an example of GPIO21, which would correspond to, what is that? Yeah, source ID 29, and that should jump. So when this GPIO21 interrupt occurs, the execution would jump from this would be the base address I have set in the empty vec, and that plus 116, it would jump here, and that can, this is just 4-byte location, or one, you can just have one instruction here. So from here, the execution would again jump into the corresponding interrupt handling function, which would be this one. But in this interrupt handling function of GPIO21, all you need to bother is how to handle GPIO21. That's it. Whereas if you have the direct mode, you have just one base address. That means for any interrupt that would jump into the base, and inside that you have to read the mcos register, and you have to find like this whether it is an exception or interrupt. Then even in the interrupt, you have to check the source ID from the claim register to figure out what, and all should be processed in this same handler. Whereas in vector, it's like uh, the branch address would be different for each source of interrupt. So recently I have been looking for some module that I can interface with my Hifive1 RevB board through SPI or I2C interface, and I came across this Crystal Fonts monochrome OLED display module. Okay, and this has 4 touch cells. I think it's like 1 and 2, 3, 4, and this can be interfaced through SPI or I2C. So this one module would be enough for me to try with both I2C and SPI interface. So for next couple of video session, I just want to interface this and write the assembly code and see if the touch cells and if I can display some black and white text on this wallet display.